and I believe it converged everywhere, if I'm not mistaken. But that's not what I'm asking for now. This function, I want us to take derivative of it. All right, I want us to take a derivative. There's a lot going on there, isn't there? There's a lot going on, looks like it. This stuff right here, all of that, bless you, is your C sub n. That's the thing that keeps on changing, the number, right, that keeps changing in front. It's the x to the 2n. That's the part that actually change, like that's the power. That's the part that has the x in it, right? So this part right here is like our x minus a to the n. So any guess as to what, I want to see if someone can kind of guess as to what this is. It's not a complete guess, but go for it. The C sub n is like a constant, so you don't differentiate that, right? It comes for the ride. So differentiate x to the 2n. What would you get? Oh, I forgot the sum. Yeah, sorry. Hold on a second. So sum. Let me leave that for now. I'm going to leave the -1 to the n over 2 to the 2n, n factorial squared. Okay, that's my C sub n. Now, go ahead. 2n x to the 2n minus 1. All that is the power rule on the x to the 2n. Everything else stayed the same because it's a constant. Well, it's a constant as we vary the n's, right? It's not affected by the x. Now, we took the derivative of a power series, so where does the index change to? What does it change to? 1. Now, you can switch to 0 because of that, but I'm just going to put 1. I just always like to play it safe.
Is it a bad idea?
There are some times when that might catch up with you. If your power series doesn't look exactly like x to the n, it could be a problem. So I always just say the index is going to go up by 1. Now, you can look at this right now. You can tell that if I plug in 0, like if I change that to 0, that's going to give me 0, and it wouldn't change the sum then, right? You get 0 if you plug 0 in. All right, that's one way to do the problem, is to do that, which is pretty nice and clean and straightforward, I hope. The other way to do it is to actually write out the first few terms of the original series. Now that might be ugly to do. Let's do it right here. What if I said let's let n be 0? What would n be 0 be? 1 x to the 0 power, so 1, 2 to the 0, and 0 factorial, 1. So 1 squared, 1. It's just 1, right? When I plug in 0, I get 1. Okay, when I plug in 1 for n, I get negative. What's on top? X squared over. Yeah, I'm plugging in 1 for n here, so 2 to the 2 is 4 times 1 factorial is 1, 1 squared is 1, so we get 1. So that's where I am, right? Yeah. Plus would be the next one. Now I'm plugging in 2 for n, right? So that's positive. We get x to what power? 4 over, it's going to start getting messy quick. N is 2, right? So 2 to the 4th power? 16. 16. And then 2 factorial. 2 squared, 4. Let's do one more. One more. Would it be plus or minus? Minus. X to the 6th over. I'm plugging in, what am I at? 3, right? Yeah. I'm at 3, so 2 to the 6th power. 64 times, all right, we're at 3. 3 factorial is 6. 6 squared is 36. All right, plus dot, 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 right? That's what it is, yes? Yeah. All right, let's see. Can we... Did this work, I guess is what I'm asking. Is this right?
it wouldn't have been right if we had said x as n equals 0, because our first term wouldn't have been negative.
What if n was 0? Wait, say again?
If we switch n to 0, like you said we could for some of them.
On this, are you talking about on the derivative?
On the derivative.
Uh-huh.
Our first term would be positive, which wouldn't agree with the original derivative.
So you're saying?
Because if you take the derivative of our solution, the first term is negative.
Okay, let's work to it. You're seeing it before, yeah, okay, so the reason I'm having you do this both ways is to see if we're getting the same answer, or if something made something not work, okay? Because we have to be careful with this. It's not as simple as, oh, just differentiate, right? So this is what we got by deducing that, oh, all we're doing is just ignoring all that and then just doing the good old power rule on that, right? That's what we're getting. But if we actually write out the terms of this series, here's the first terms, right? And everyone agrees on those terms? Let's differentiate this now, right? Take the derivative. What happens when you differentiate this? 0. Okay, here, differentiate. So I'm taking derivative right there. It's going to be 0. And then differentiate, you get negative. And then 2 comes down. I'm going to put 2x over 4 times 1. I'll clean that up if I need to in a minute. The next one will be plus 4 comes down, x to the third over 16 times 4, right? That's what's happening. See, these are just, all these denominators are just numbers, so I'm ignoring them, and I'm just doing power rules on the top. Next one is minus 6x to the fifth over 64 times 36. This is the derivative. Is that what our formula gives us, though? Yeah, so let's check it. Let's plug in n equals 1 to this. What happens if you plug in n is 1? Negative 1 over, plugging in 1, right? So 4, and then 1 factorial, squared 1, and then times 2 times 1 times x to the, what? First power? Is this? Yes, it is, right? The first one worked. Let's check another one. But now plus, okay, if we plug in n is 2, we get 1 over 2 times 2 is 4, 2 to the fourth power, 16 times 2 factorial is 2, squared is 4, and then we have times 2 times, we're at 2, right? 2 times 2 is 4, x to the, 2 times 2 is 4, take away 1 is 3. And we could keep checking. It matches up, right?
So the reason this works is because n is treated as a constant and we're taking the derivative of x, so it just naturally falls into place as the derivative of the whole thing.
Wait, the n is a constant. Say again?
So because we're treating n as a constant, you can take the derivative, you peel off the x, and you take the derivative of it, and the whole thing ends up being the derivative.
This right here, every time I plug in an n, right?
N is a constant? Yeah, so
When I plug in an n, this becomes a constant, right?
okay.
And then I have x to a constant power. And so when I take the derivative of a constant times x to a constant power, you do the power rule. And the constant that's in front just comes along for the ride the whole time.
That makes sense. I'm caught up now.
Yeah. All right, so just trying to verify, we have to be careful, right? Just trying to verify that doing it with the power rule, bringing that 2n in front of the x and subtracting 1, that does in fact give you the same thing as if you wrote out the terms and then differentiated it term by term. The way you do it is up to you, okay? And there's sometimes it's better to do one way over the other. It's easier to do one than the other. So I wanted to show you both of them. Let's see here. Yeah, this is where I'm not going to go. I will do this one, though. So we are skipping in the notes example, what was it, 4 through 6? If you're interested in those, I've got other videos on my YouTube channel. Just go look up my playlist, look up Cal 2 lectures, and you can find it. But I am going to get straight to this one here. What's the antiderivative of that? Okay, well let's ask the computer for it. Because you don't have a method to do that. You don't know how to integrate that, neither do I, right? We don't have a method. 1 over 1 plus x to the 7th power. No, there is a way, somehow. Okay, so there is some way through. Yeah, no, thank you, right? No, thank you. So there's no error function here, right? There's no error function, so there's a way through it. It's probably some weird stuff that you would never think to do. So is there another way of doing it? Well, one thing I could do is I could say, all right, if I do the integral if I do this expression and I rewrite it as 1 over 1 minus negative x to the 7th, like that, using this, right? Then that will be equal to the sum n equals 0 to infinity of negative x to the 7th to the n. So long as what? The absolute value of negative x to the 7th is less than 1, which really gives us a pretty narrow restriction on when this is valid. But at least I've got something, right? I can go to a series. So that means the original integral, right? We're doing the integral of this series. See, all I'm doing is replacing the integrand with its power series representation. And I want to clean this up a little bit more. I'm going to rewrite it as negative, oh, I forgot the n. I'm sorry. I forgot the n over here on this one. I didn't forget it over here, but I forgot to put it over here. So negative 1 to the n, and then x to the what? 7n. Then dx, right? All this means is go find the antiderivative of that, right? Go find the antiderivative of that power series. And we have two different options. We can either write out this power series, right? We can write it out and then do the antiderivative of each term, or we can use the formula that allows us to do that quickly right here at this step. I think that's the way we should go, right? The antiderivative of this should be c, some constant, plus the new series. And I'm using the power rule on x to the 7n. Right? I'm using the power rule on that. Antiderivative power rule. So what's the antiderivative of that? 1 over 7n plus 1, x to the 7n plus 1. And then the negative 1 out in front stays. I am only taking the antiderivative of the part that has the x in it, right? This is our constant that comes for the ride each time.
So any chance you have to take out negative 1 to the end, you should do that.
Yeah, you're trying to get x to a power. You don't want negative x to a power, because then that'll throw things off. All right, let's actually write out the first few of these terms. Okay, let's plug in, see, c plus, if n is 0, we get a positive, right, positive, and then we get 1 over, n is 0, 1 over 1, 1, right, and then x to the 1. So we just get x. The next one should be negative, because now we're plugging in 1, so that's negative. If we plug in 1 down here, we get 1/8, right? 7 times plus 1/8. X to the 8th. Okay, plus, next one. 1 over, okay, we're plugging in 2 for n. 15, 1/15th x to the 15th plus dot, 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 right? That keeps going. Which, had I written this out, I didn't do this, okay? But had I written this out, showing you like the other option, had I written this out, if I let n be 0, I'm going to go really fast here. If n is 0, this is just 1, and then minus, if n is 1, x to the 7th, then plus, it'll be x to the 14th, and then it'll be minus x to the 21st. That's what would happen if you just wrote out these terms. And the antiderivative of that is x, and the antiderivative of that is negative 1/8 x to the 8th, and the antiderivative of that is that. Right? So I could have done it, I could have done it either way. So I'm going to now go back to the computer, and I'm going to scroll down. There's that answer. But if I scroll down, it probably gives me the series answer. Holy crap. Definite integral? No. Gave me a definite integral. I didn't ask for a definite integral. For some reason, it's not giving me this series. Huh. Well, I'll just come up here and say series then. Really weird. Normally, it gives me the series answer. Maybe I scrolled over it too fast. Now it doesn't want to give me anything. I want the indefinite integral. I don't know, it's not doing it. Weird. Okay. It is what it is. Right? We have this, we have the series answer, right? So if you were to take a value, as long as that's true, then this is a valid answer. You know, it's an infinite series. Now, I would agree with you that that window is really, really small. So it's not very, very good, but again, the idea is more that you can take a function and convert it into a series. So that if you can't integrate it by hand, you can at least integrate the series. Right, do y'all agree that if you have a power series, differentiation, integration is pretty straightforward? Just power rules, right? Differentiation, power rule, integration, power rule, right? So if every if every function can be converted somehow into a series, then that makes it very useful to us. Differentiation, integration. So we're going to move to the next section now. And this is the big section, because this section says, okay, all right. What if we just have a function, any function, and we want to find its power series, right? Is it possible to do it? And the answer is yes, but there are some conditions. We do have some conditions that are going to restrict what we can and can't do, but for the most part, we can. And the motivation for this comes from something that we were trying to do, we as in humans were trying to figure out for a long time. So let's start with this example. We all know what this function is, right? F of x equals sine x. And there's nothing wrong with that function. We love that function, right? We love it. Sine curve, everything's great, right? But is there a power series for that, right? That would be a natural question at this point. Is there a power series that I could use instead of that? So here's the approach that we took as humans, I guess, is we said, let's try and approximate that function. Let's approximate it. I'm going to pick a function. I'm going to call it g of x. And it's going to be approximately that function. Approximately. Well, would you agree that whatever that function is over there, let's put some restrictions on this. Let's say that this g of x that we're going to pick here must be a polynomial. Because that way it'll look like a power series, right? A polynomial. So can I pick a polynomial that would be really close to this? Would you agree that when I plug 0 into this, I should get the same answer as plugging 0 into that? And when I plug in, when I take the derivative of this and plug in 0, I should get the same thing as taking derivative of that and plugging in 0. And when I take the second derivative of this and plug in 0, I should get the same as the second derivative over there. In other words, if I want these two things to look, look the same, then at some point, let's say at some point A, they should match, they should both go through that same point, right? They should also both have the same slope of a tangent line at that point. And they should both have the same concavity at that point, second derivative. And then third derivative, which we don't really talk about what third derivative is visually, but the third derivatives should match, and the fourth derivatives should match, and the fifth derivatives, and sixth derivatives, and seventh derivatives, right? Should match. The more they match, the closer they are to being the same function. Yeah? So let me see if I can, let me see. I'm going to do, let's not do a quadratic. Let's do a cubic. I'm going to go with the cubic polynomial. Just a generic cubic polynomial. And I'm going to see, can I make that cubic polynomial approximate that? Cubic would look like this: ax squared plus bx, ax cubed plus bx squared plus cx plus d. There we go. That's a cubic polynomial. I'm going to try and find right now a, b, c, and d that would be pretty damn close to that function, at least at one point. So here's the first thing I want. I want that f of 0 be equal to g of 0. Right? I would really like that to happen, that when I plug 0 into both these functions, I get the same thing. Well, what happens when I plug 0 into this? What do I get? What sign of 0? 0. What happens when I plug 0 into that? What do I get? D. So then now I know what D is. So D needs to be 0. In order for these two functions to actually have the same value at 0, I need that D to be 0, right? Good. I know one of the four things. Now, what else do I want? I'd like the slopes of the tangent lines to be the same as well. So I want the derivative at 0 to be equal to the derivative of that one at 0. What's the derivative of this? Cosine, right? And what happens when you plug? You know, it might be worth it for us to list out the derivatives of f. Here's, let me do it this way. Here's f, f prime, f double prime, f triple prime. I need a few of these. F. Once we get past 3, we like to put the number, like 4, in parentheses. So f is the sine function. The derivative is cosine. The second derivative is negative sine. The third derivative is negative cosine. And then we finally get back to sine again. And then it's just going to continue repeating, right? So I wanted the function at 0 to be the same, right? Got it. Now the derivative of f, which is cosine, what's that plugged in 0? So cosine of 0, that must equal to this, right? This is 1. Cosine of 0 is 1. So I need g prime of 0 to be 1. I need the derivative of that function over there to be 1 when I plug 0 into it. What's the derivative of this? 3ax squared plus 2bx plus c, right?
I like that plus.
Yeah, and if I plug 0 into this, what happens if I plug 0 into this? I get c. So when you plug 0 into the derivative, you get c. So I need c to be 1. See, again, I have the sine function. I'm trying to approximate it with a third degree polynomial. Right? Is that a question? I just picked it. I could have gone 4th degree, or 5th, or 6th. Ultimately, I'd like for this to be an infinite polynomial, right? Because then that would be a power series. So I know that if I go 3rd degree polynomial, D should be 0. C should be 1. Let's keep going. I would really like, right, I want the second derivatives to match at 0. Oh, sorry, that's G double prime on this side. All right, what's F double prime? Negative sign, right? And what's sine of 0? 0, so negative 0, 0. So the left side is 0. What's G double prime? I need to write it out. 6ax plus 2b. So what is the second derivative if I plug in 0 for x? 2b? So 2b must be 0, which means that b must be 0, right? So I know what d should be. I know what d, c, and b. I know what all of those should be, right? One more. I want that the third derivative at 0, f, be equal to the third derivative of g at 0. What's the third derivative of f at 0? Negative 1. And the third derivative of g, which I hadn't done here, is 6a. 6a, that's the third derivative of that function, 6a. So 6a must be equal to negative 1, divide, a should be negative 1/6. And that's it. I'm not going to go anymore because I went with the third degree polynomial, right? If I would have gone fourth degree, I could go one more derivative because I would have 5 variables I'm solving for. But as it stands, what I'm saying is that if I want to approximate this function with the third degree polynomial, then what I'm going to do is I'm going to use this one. A, which was negative 1/6, x to the third, plus what was b? 0, so I'm not going to put a b there. C was 1, and then d was 0. So that's it right there. That's my polynomial, my third degree polynomial. You want to see it? Okay. Here's sine x. I'm going to zoom in kind of close to 0 because remember, we were trying to get these things to match and look the same near 0, right? If I want them to match closer to somewhere else, I would have used a different number here. All right, it was x. Well, yeah, negative. I was going to do it the other order. Can I do it the other order? Where is it? It's right there. Okay. Can I do it in the other order? I'm going to go backwards. I'm going to go x first, and then minus 1/6 x cubed. I'm only doing that because that's the way series work, right? They start and the powers get bigger. So I'm going to go x minus x cubed over 6. It's pretty close, right? At least near 0. At least near 0, these are pretty damn close. And once you start going a little bit away from 0, it's not that good of an approximation. Actually, wasn't it pretty good before I even put the x cubed in there? Like at least near 0.
Yeah.
Look at that, they're pretty close to the same function. Which is why in a physics class, you'll see in a physics class that you can replace sine of x with x so long as x is really small. So like if x is small enough in a physics class, we will say, you know what, let's not deal with sine x. It's going to make things nasty. Just replace that with x. But it only works if you can guarantee that the x is small. And you can see it from the picture. They're essentially the same functions near 0. Once you go past, get a little bit bigger, you can't, right? So I'm going to put that piece back in. What would have been better is if I would have maybe done a 4th degree polynomial, or a 5th degree, or 6th, or 7th, or 8th, or 9th, or 10th, right? Yeah?
Fourth degree polynomial would have given you, I predicted 0.
Yeah, the 4th degree would give you a 0. So it wouldn't help. Then the 5th degree would give us another piece. All right, so do you get the basic idea is that what we're doing is we're taking a function and we're saying, hey, is there a way that we can fit a polynomial to this function? At least near a point, yeah? So I put here, we've seen how we can use that one formula in the previous section, the 1 over 1 minus x thing, but it's very limiting. We're going to try and open up what we can do. Some things that you might see in the future, sine of x is approximately x. I just showed you that, right? You can do the same thing we just did, but for the cosine function instead, and do a polynomial, like a 4th degree polynomial, and run through the same thing we just did. And you can show that cosine x is approximately 1 minus x squared over 2. If you graph these two together, they're pretty close near 0. All right? Whoa. So I want to write this down. Given some function, right? Somebody gives you a function. Can we find this? Right? If someone gives me a function, can we find a power series that represents that, right? Can we? That's the big question. Give me a function, sine, give me e to the x, give me some function. Can I find the power series for it? Well, what is the only difference when you look at one power series and another power series? What is the only thing that changes between power series? It's the only thing that makes them uniquely different from one another. It's the constant in front. It's this. This right here dictates everything. The formula that generates those numbers is the thing that makes one power series look different from another. All of them are going to have powers of x. Now, you might only have even powers or odd powers, or maybe you'll have all even and odds, or maybe there will be skipping like every 4th power or something, but they're all going to have powers. You might have zeros out here in some instances, but this is the thing that controls the entire power series, that right there. So we're going to study right now what are called Taylor and Maclaurin series. Basically, the idea was this. Taylor was, I believe, the person who figured this out first. I could be wrong there. That the way you can figure out this formula. You can actually figure out what this formula is, as long as somebody gives you the function and you can continue to take derivatives of it. All right? So I'm now going to show you how you can develop the formula for this. Do you all agree that if I have a function and then from that function I give you a formula for c sub